L'Hopital or other, finding derivatives and second derivatives, and finding max and mins. And of course, second derivative test was a biggie last time, I think. So, in response, let's see. If f prime of A equals 0 and f double prime of A is greater than 0, that implies that point is a minimum. That is A f of A. Or f double prime of A is less than 0, that implies that we have a maximum at A comma f of A. And finally, or f double prime of A equals 0, and that implies the test fails. So we don't know if it's a max or min or neither. All we know is that at that point, if you're driving a car along the road that is the function, at that point the wheels are straight. The steering wheel is straight, the wheels are straight. Okay, let's look at, now that we know how to find max and mins, let's start optimizing. And the best way to do optimization problems is just start attacking them. So the first one I'll do is the easy one. If I have a standard 8.5 by 11 piece of paper, I have other ones in there, and I cut a square out of each corner, x by x, and then fold the tabs up, tape it together or whatever. I end up with a rectangular open top box and if this is 11, it's 8.5 inches. Then the length of that box is 11 minus 2x. The width of that box is 8.5 minus 2x. And the height of the box is x. That is the volume is length 8.5 minus 2x, actually width, times length 11 minus 2x times height x. Doing the arithmetic there, let's see, we have x times 4x squared minus 22 and minus 17 minus 39x, and then 11 times 8.5, 88 plus 5.5, 93.5 plus 93.5, the volume is, or the volume is 4x cubed minus 39x squared plus 93.5x. Okay, and anytime we're doing application problems like this, what we, for the function v equals 4x cubed, etc., etc., the domain is all real numbers. But if we look at the sheet of paper, we cannot cut a corner out of here that's 18 inches by 18 inches. The largest we can cut out is up to 4¼ inches. And we can't cut a negative value out, so the implied domain on this is from 0 to 4¼ Any values we get beyond that are not answers to the problem at hand. So let's go and find the derivative. dv dx is 12x squared minus 78x plus 93.5. And we set this equal to 0. 12x squared minus 78x plus 93.5. And it doesn't factor, so we throw it in the quadratic formula. X is equal to minus b plus or minus the square root of b squared minus 4 times a times c, okay, all over 2 times a. So you can multiply all that out by hand, but I think I'm going to use a calculator to find the values of x. So F2, first line says solve, comes up like that. Then you put in what you want to solve, 12x squared minus 78x plus 93.5 equals 0. And what variable are we solving for? Comma x close. Makes life pretty easy if we have that. Clear all this stuff I did this morning. F2, solve. And we have 12 times x squared minus 78 times x plus 93.5 is equal to 0, comma, solve for x, close, and we crunch this out and it throws the answer out. It says x is equal to 1.5854 17970 38 out to a lot more places than we need. And the other answer it gives got lost there someplace. Okay, what'd I do? What did I do? Escape. There we go. Okay. And the other answer says x is equal to 4.9145. 8202 and change 962 or values in that vicinity. Okay. Now, first off, let's observe that x is greater than 4 1/4. So it does not apply to our problem. It's a perfectly good answer to that quadratic, but it's not a good answer for our problem. So answers that are good for the algebra involved or the calculus involved that do not apply to the problem we call extraneous. We have another one. Now, is that a maximum or minimum? Well, what do I do is find the second derivative. The second v dx squared is 24x minus 78. Well, that's about 1.6. 1.5 times that's 36. Add another 2.4. So it's about 38.4, which is minus 78 is clearly negative. So at f or v double prime at 1.58 change is clearly less than 0. So if the slope is 0 at this point and the second derivative is negative at this point, then this gives us a maximum. And that maximum value is achieved by putting this x into that equation, or this equation. seeing what that is out of curiosity. Okay. Clear. Enter. Let's get rid of a bunch of this. Get rid of the extraneous one. Go to the front. Get rid of the x equals. Okay. So I have put that value into the calculator, and now I'm going to put it in here. Okay. 4 times previous answer cubed minus 39 times previous answer squared plus 93.5 times previous answer. That tells me that the volume is somewhere in the neighborhood of 66.148. So the volume at 1.5854 is approximately, is approximately 66.148 cubic inches. Now, this may be the most practical problem you ever get out of calculus, because how many of you work in some office setting or around other people, and occasionally someone puts a bag of popcorn in the microwave. That bag of popcorn is just a little too much for one person. So they're usually nice and say, would anybody else like a little popcorn? You've made your box ahead of time, say, oh yeah, put a little in here. So by doing this, they are generous, they fill up your box. You get the most popcorn of anybody else he gives popcorn to, because they just have a flat sheet of paper and it doesn't. So, keep the popcorn. Now, having said that, we can actually increase on this volume, but it's not at this level that we can solve that yet. But instead of cutting square corners, we can cut like V's in each corner. And fold that up, and you end up with a nacho tray. And given the proper angle and the proper depth of cut, this will have slightly more volume than that. Again, we're not solving that one today. Okay, so let's look at one just a little tougher. Let's turn to the problems in section 4.6 and work through these. Talk about max and mins. So they begin on page 270, and what was I looking at first? Let's say number well, let's do number 7. It's a pretty standard one. The best fencing plan on page 270, number 7. A rectangular plot of farmland will be bounded on one side by a river and on the other 3 sides by a single strand electric fence. With 800 meters of wire at your disposal, what is the largest area you can enclose and what are its dimensions? Now we do have to make an assumption. Is that the river is straight. Because we're putting a fence up here. And length plus 2 width length plus 2 times width is 800 meters. And the area that this encloses is length times width. Well, that has 2 variables. So we go up to this equation and say, hey, look, I can say the length is equal to 800 minus 2w. So let's put that down here. Area is equal to 800 minus 2w times w. And now this area is in terms of a single variable. Do the arithmetic. Area is equal to 2w squared minus 800w. That's not right. Area equals minus 2w squared plus 800w. And if we take the derivative of both sides with respect to w, dA dw is minus 4w plus 800. Set this equal to 0 is equal to minus 4w plus 800. Move the 4w to the other side. Divide by 4. W is 200, which means L is 400. And the area is 800 square meters. That's a little larger than the average garden plot, but that works. So, any farmers in here by chance? All city folks? Interurban, suburbs? Nobody ever grew up on a farm? Know what a cow is? I one time took a group of high school students down to the Wichita Wildlife Mountains. And one of the students with us had never seen a live, large, 4-legged animal. A horse, a cow, a bison. And then when we were driving up Mount Scott, she was hugging the floor. Thought for sure we were going to die because we were going so high. High school student. Had grown up in northeast Oklahoma City and never been out of town.
The bad thing is Mount Scott is nothing. Mount Scott's nothing.
Exactly. Yeah, when I was 13, I made it from bottom to top in 20 minutes. Of course, then I was part mountain goat when I was 13. I think at 13 I weighed 72 pounds. I'm a little heavier now, by a factor of 3. Ooh. Okay. Well, let's look at number 24. We have a trough, and it's a trapezoidal prism. The trough in the figure is to be made to the dimensions shown. Only the angle theta can be varied. What value of theta will maximize the trough's volume? Well, basically, we have a trough, which 1 unit, 1 unit, 1 unit, and some angle theta. And then I'm foreshortening this, but that's 20 feet. Each of these is 1 foot. Okay. So what will the volume of a prism? The volume of a prism is the area of the base times the height. Or in this case, area of the face times the length. So this is constant. So it's not a variable, it's 20. All we have to do is worry about the area of the base. So let's maximize the area of the base, and by maximizing the area of the base, we will maximize the volume of the trough. Okay. So, the area of the base is 1/2 the sum of the bases times the height. Different height than this is 20. Well, the height is 1 times the cosine of theta. 1 times cosine theta. One base is 1. The other base is 1 plus this plus that. Those are both 1 times sine theta. So we get 1 plus 2 sine theta. One base, the other base. So the area is 2 plus 2 times 1/2 is 1 plus sine theta times cosine theta. That is, area is cosine theta plus sine theta cosine theta. Okay. So now let's find the derivative of A with respect to theta. dA d theta is minus the sine of theta plus. This is a product. Derivative of the first times the second gives me cosine squared theta. The first times derivative of the second gives me minus sine squared theta. Set this equal to 0. Minus sine theta plus cosine squared theta minus sine squared theta. Remember your trigonometry. Trigonometric equations are pretty easy to solve algebraically if it's all the same function. Well, we have 2 different sine terms and 1 cosine term. Fortunately, it's cosine squared, so we replace cosine squared with, what do we substitute for cosine squared? Your fundamental trigonometric identity. Sine squared plus cosine squared equals 1, so cosine squared is 1 minus sine squared. 1 minus sine squared. Now this is a quadratic in terms of sine. And so I get 1 minus sine theta minus 2 sine squared theta. We set that equal to 0 and factor 1, 1. One of these is 2 sine theta, the other is sine theta. Now let's pick our signs carefully. I want that to come out negative, so I'll pick this one to be negative, that one to be positive. So that says that the sine of theta is equal to -1, which means theta is 270 degrees, or minus 90 degrees. And if we look at minus 90 degrees, if we bend this over minus 90 degrees, it folds into here, this folds into there, and we have 0 volume. So let's look at the other one. This says twice the sine of theta equals 1. Sine of theta equals 1/2. Theta equals 30 degrees. So if theta is 30 degrees, then we can do the dimensions on the face of the prism. This is 1. Sine of 30 is 1/2. Cosine of 30 is square root 3 over 2. So the top is 2, the bottom is 1. The area is 1/2 the sum of the bases times the height so the area is, what is that? 3 times square root 3 over 4. And the volume is 3 times square root 3 over 4 times 20, which is 15 times square root of 3 cubic feet. Number 22 is an interesting one because they don't give us any dimensions. But they tell us a window is in the form of a rectangle surmounted by a semicircle. The rectangle is clear glass, whereas the semicircle is of tinted glass that transmits only half as much light per unit area as the clear glass does. The total perimeter is fixed. Find the proportion of the window that will admit the most light. I'll start over here on this first board. Draw the picture and start figuring out some relationships. We call the radius of the semicircle r. That means the base, or the length of the rectangle, is 2r. And what we don't know is, in this picture, is the height of the rectangle. But we do know that the perimeter is fixed. So it has a fixed perimeter. Well, what is the perimeter? The perimeter is 2r plus 2h plus pi r. Semicircle is pi r. So the perimeter is 2r plus 2h plus pi r. Solving for h, we have p minus 2r minus pi r over 2 is equal to h. Now we can express the area easy enough. But I don't want the area. I want light transmission. Effectively, the light transmission here is 100% of some constant times the area. Here the light transmission is some constant, same constant, but 1/2 this area. So the light transmission is 2r times h, p minus 2r minus pi over r over 2, that's length times width, plus half a circle, pi r. Now, I'm sorry. We want the area of the circle. Area of the circle is pi r squared, but I want half that area, pi r squared over 2. If I only want 50% of that half, so it's pi r squared over 4. So this equation represents the amount of light that's transmitted as a function of area. And let's go on and distribute. L is equal to PR minus 2R squared minus pi r plus pi r squared over 4. That's actually quadratic, so we could use algebra to solve it. But we'll go on and, because remember, if we have a quadratic, and actually this factors, so we actually have a linear. So let's factor in r. We have r times p minus 2r minus pi plus pi r over 4. Those are the two values that, if r is 0, we have no, we have an infinitely tall, skinny, not infinitely tall, but straight up, straight down, not very interesting. Or if it's this value, then we have something pretty wide but low, and again, not very interesting. So, but let's go and take the derivative of this with respect to r. dl dr, dl dr, not r, dr is equal to p minus 4r minus pi plus pi r over 2. Set this equal to 0. Take these two terms to that side. Well, p minus 4r minus pi plus pi r over 2. Take the r terms to the other side, and we get 4r minus pi r over 2 is equal to p minus pi. Factor the r is equal to p minus pi divided by 4 minus pi over 2. So that's r with respect to p. And h with respect to p, we would put, where we solve for h, we put the r value back in here, which essentially solves the problem. It asks for the ratio of the dimensions, but we have the dimensions because plug this back in, and we have h. And if we form the ratio of 2r to h, then we have the ratio they're talking about. Okay, let's look at another one a little different. It starts out, if you turn the page, I think, page 272, I think it shows. Oh, no, page 273, number 42. Says a cone is formed from a circular piece of material of radius 1 meter, by removing a section of angle theta and then joining the two straight edges. Determine the largest possible volume of the cone. Okay. So here, if you start with a circle and you cut a chunk out, theta, then bring that together and you get a cone. Whose slant height is 1. And what I need to find is the radius and the height. Well, the radius is interesting enough. What is it? What is the circumference of the original circle? What is the circumference of the original circle? With a radius of 1. The circumference is 2 pi r. So the original circumference, 2 pi r. But we cut a sector out of it, but I'm not interested in the entire sector. I'm interested in that little bit of length. And arc length on a circle of radius r, little s, is equal to r times theta. In our case, since r is 1, that arc length is theta. So removing theta leaves the circumference here 2 pi times 1. 2 pi r minus theta. So that's the circumference. If we know the circumference, can you find the radius? Yes. This radius is its circumference divided by 2 pi, which is 1 minus theta over 2 pi. Two pi r is the circumference, so the circumference divided by 2 pi is the radius. So I have an expression in terms of theta of the radius. Looking at the cross section, the height is the Pythagorean relationship between the slant height and its radius. So the height is the square root of 1 squared minus paren 1 minus theta over pi squared. Doing the arithmetic under the radical, h is equal to 1, subtract 1 goes away, we have a middle term which would be minus 2, that's 2 theta here, I'm sorry. Minus a minus be plus 2 theta over 2 pi plus it'll be minus theta squared over 4 pi squared. I think I did the arithmetic right. Please check it. So, now that we have the height and the radius, the volume of a cone, one-third pi r squared h. Our volume is 1/3 pi r 1 minus theta over 2 pi squared times h square root theta over pi minus theta squared over 4 pi squared. Here's my volume. So all I have to do now is find its derivative, set that derivative equal to 0, and see what falls out. So, this is a constant. dv d theta is the constant 1/3 pi. This is a product 2 times 1 minus theta over 2 pi to the first times the derivative of this, which is minus 1 over 2 pi, times the radical theta over pi minus theta squared over 4 pi squared, plus one minus theta over 2 pi squared times derivative of this. That's a square root, so I get 2 times the radical theta over pi minus theta squared over 4 pi squared times the derivative of the what's under the radical, and that will be 1 over pi minus 2 theta over 4 pi squared, or 2 over pi squared. Now that looks scarier than it is, because when I set this equal to 0, I can get rid of quite a bit of it. I set that equal to 0 and divide by this term, that leading coefficient goes away. Also, if I multiply both sides through by this radical, then that goes away, and this square root goes away. So when we do all that and set it equals 0, we have 2 times 1 minus theta over 2 pi, close, times minus 1 over 2 pi, times theta over pi minus theta squared over 4 pi squared, plus 1 minus theta over 2 pi 20 squared over 2. Oh, times 1 over pi minus theta over 2 pi squared. So I'm not going to go on and solve this, but you see now that we have a single equation set equal to 0, and we can put it into our calculator again. Use our F2, and first thing on there says solve, paren, we put all of this in here. I would change the theta to x, comma x, close, and let it crunch away. And this is what? Third degree in theta. So potentially there are 3 solutions. I can give you 2 of the solutions immediately. One solution is theta equals 0. If theta equals 0, our cone has a radius of 1 and a height of 0, has a volume of 0. Our other is our theta is essentially 2 pi, and we have no circle left. Or, the limit of that, as it approaches 2 pi, you have a very tall, skinny cylinder, which essentially is almost 1 tall, and almost 0 wide. So the volume is 0 again. So those are the 2 extremes. So the third solution is when that doesn't equal 0 or 1, whatever that might be. Let's do another of those. I'm looking now at number 45. Shortest beam. 8-foot wall, very tall building, 27 feet from the building. Okay. Here's my picture. I have an 8-foot fence, 27-foot clear space, a tall building. Okay. The supposition is that it's level ground. Somewhere in here I put a beam across the top of the fence all the way up to the side of the building. Now, if I started the beam further out here, then you see that it would be longer. Or if I started the beam closer in, again, it would be longer. Question is, what angle to make that the shortest as possible? Let's call this X. Let's call this H. And we look at the small right triangle, 8 by X. And we look at the large right triangle, 27 plus X by H. They're similar. So I can say, I'll say it this way, X is to 8 as X plus 27 is to H. I can solve for H in terms of X. H is 8 times X plus 27 over X. The length of that beam is the square root of X plus 27 squared plus 8 times X plus 27 over X squared. So once that's set up, we're ready to go to work to find the length of the beam that is as short as possible to fit nicely. I don't have to find theta. I have to find the length of the beam. Once you know the length of the beam, you can find theta, but we're just looking to go for the length of the beam. So, here we go. dl dx equals, what's the square root? 2 over radical times derivative of what's inside, 2 times X plus 27 to the first, times derivative of that, which is 1, plus, this 8 is a get squared at 64, but we get 64, oh, this is a quotient too. Whoop. I'll do a little arithmetic here. Derivative of the numerator is 8 times, oh, it's just 8. Oh, that's right. $64 times X plus 27 squared will be twice 64, 128 times X plus 27. Derivative of the numerator times denominator minus numerator 8 times X plus 27 close times derivative of the denominator, or times 1 all over, I have this radical, let me move this down a little bit, over X squared over twice the radical. The reason I'm not writing that radical down is because I'm going to set things equal to 0. If you set things equal to 0, the denominator can go away. And additionally, I can multiply through by X squared. So I'll get 0 is equal to 2x squared. I'll multiply by 2 times that, so it's gone away. 2x squared times x plus 27 plus 128 times x plus 27 times x minus 8 times x plus 27. this is cubic in x. So it has 3 solutions. One of them will be a minimum, and the other 2 will be, well, x will be very, very large, or very, 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 very small, and should approach 0, I don't know, and it should approach forever. But again, there we have a cubic. When you find set it equals 0, use your solve function on your calculator to find value of x, and once you have the value of x, then you can find the value of h, and knowing those 2 lengths, you can find the Pythagorean relationship, find the length of the beam. Another classic problem similar to that is you have a hallway with a square corner, and the width of this part of the hallway, let's say, is 8 feet. The width of this part of the hallway is 10 feet. And the problem is, what is the longest object you can carry down the hallway and make that corner? Now this ignores a few things like the thickness of the object. And also ignores that you're not crawling down a thin tunnel. You have a ceiling. So you can pick one end up higher, which effectively shortens the projection. So you can make so if it's very high ceiling, you can get something quite long through there. But if it's 8-foot ceiling, then you still have constraints. It's basically diagonally from here to here to here, 8 feet up, would be your constraints. So it's an interesting problem too. I don't think they have one like that in the text. I think there's one more I want to look at. Maybe, maybe not. Let me think. No, that's the last one of those I wanted to at least set up in class. What I want to look now is section 4.7, and I'm just going to talk about it briefly, kind of sketch out what it does, because it's not on the syllabus. But the reason I want to talk about it just briefly is because it is important for, I mean, to solve these equations, we use our solve function on our calculator. But if you think back in Newton's day, in order to solve a higher degree equation, they didn't have a nice method to solve them. So Newton came up with a method that often will give you a respectable answer. If I have some curve, I'm looking for the zeros of this curve. Okay. Now this is a cubic. There is in fact a formula that will give you those. So this may or may not be a cubic. It might be a quintic or something. And if it's a quintic, there's not a general solution for it. But Newton says, well, look, here's what I'm going to do. I'm going to pick a value, it's easy to find. Say here, call that x naught. And, of course, f of x naught. And f prime at x naught. Because f prime at x naught, through the point x, f of x naught, gives a point slope equation of a line, the tangent line. Tangent line crosses the x-axis. You can find that value rather easily. Then you plug that value back in the function. This is x1. And it gives you an f of x1. And an f prime of x1, which gives you a tangent line back. And each time you do this, you get closer and closer to that point. Now manually, the decimal places start filling up rather quickly. So manually, it's difficult. But this can be programmed into a calculator. However, there's some danger in this as well. Let's suppose I'm looking for this point. Okay. I pick a point here, take my tangent line, it hits here, take my tangent line, it hits here, which brings me back to that point. So there are some points that are harder to find. You're limited in the space in which you can actually search to get the result that you need, depending on where the inflection points and things are. I can find this point from this side, do a tangent line down, gives me a point, tangent line down, gives me a point, so it marches in closer and closer. But often that middle one is hard to find, because sometimes in finding it, it kicks you over to the next point one way or the other. But this is called Newton's method. So, officially at this point, you know everything about derivatives that I know. Having said that, that's probably a lie. But we've covered a lot of derivatives. We have not covered the hyperbolic functions, which get covered a little later, but we've covered the trigonometric functions, logarithms, exponentials, polynomials, rational functions, all kinds of powers, roots. So, what if I want to undo that? I start with something like 3x squared minus 4x plus 5. And this is the derivative. What is the original function? What is f? Well, let's just do a little thinking. Can you think of a simple function whose derivative is 3x squared? X cubed. Can you think of a simple function whose derivative is negative 4 times x? Minus 2x squared. Can you think of a function whose derivative is 5? 5x. So, the derivative of f is 3x squared minus 4x plus 5. But how about this one? X cubed minus 2x squared plus 5x minus 4. How about this one? X cubed minus 2x squared plus 5x plus 11/6. What's the derivative of that function? This. What's the derivative of that function? This. So we cannot be sure what the correct answer is. But one thing we know is whatever the correct answer is, it is vertically nested with all the other possible answers. This is a cubic. So again, let's sketch a cubic, and another cubic, and another cubic, and another cubic. And at any point x, the slope here is the same as here, the same as here, the same as here. The derivative of this function is the same as the derivative of that function, same as the derivative of that function, same as the derivative of that function. If my art was any good, the same as the derivative of that function. So when we're talking about what we're going to call antiderivatives. Antiderivatives always include an arbitrary constant, c. Doesn't have to be c. You can call it anything you want. So, let's write down a few derivatives. F prime. X to the n is n times x to the n minus 1. E to the x is e to the x. Sine of x is cosine of x. Cosine of x is minus sine of x. Natural log of x is 1 over x. Okay. That's a few. Let's go the other way. F prime back to f. Let's say I have x to the n. What function has derivative x to the n? Well, when we're going down, this exponent is 1 less than that exponent. When we're going up, this exponent will be 1 more than that exponent. But I want the coefficient to come out right as well. If I take the derivative of what I show up there now, x to the n plus 1, I get n plus 1 times x to the n. I don't want n plus 1, so I divide by the new exponent. E to the x is easy. Oh, by the way, plus c. E to the x is easy. E to the x. How about the cosine of x? It's easy. Sine of x. How about the sine of x? What is its antiderivative? Well, a reasonable candidate is cosine. But the derivative of the cosine is what? Negative sign. So to get a positive sign out of it, I start with a negative cosine, or I end with a negative cosine. Derivative of this is that. And logarithm. 1 over x. What's the antiderivative of 1 over x? No tricks here. Well, there is a little one. Absolute of x. I won't explain that absolute yet now, but the function 1 over x is defined for all real numbers except 0. So we would like its antiderivative to be true for all real numbers except 0. And to ensure that we have values, we use the absolute of x. If we look at 1 over x, it's this and this. And the value at this x there is the same as the value for this x there, except that's negative. So when we take, but anyway, that's kind of why they put the absolute on there. Plus c, plus c. Okay. So, we have been, in one sense, tearing down functions to find out what we can find out about them. Now we're going to start with the pieces, so to speak, and build up, find what these are. And this process is called anti-differentiation, antiderivatives. And the symbol for that is a very elongated S. This is the notation of Leibniz, not Newton's notation, but Leibniz's notation. We put the function in here that we're trying to undo with reference to what variable. And this is equal to some other function plus a constant such that the derivative of this other function is equal to that. So that's the name of the game. So let's look at some of those in section 4.8. On page 283, they give us a table of values, or a table of antiderivatives. So let's go to 287 and just jump into the problem. I'm going to start with number 4. And they kind of piecemeal A, B, and C so that you get the idea of how these things build. Number 4a says I have a little function, 2x to the what? Negative 3? So, 2x to the negative 3, the antiderivative with respect to x. What's a rule for x to the n? A rule for x to the n is n increases to n plus 1. What's 1 more than negative 3? Negative 2. X to the negative 2. What else does our rule say over there? Divide by the new exponent. Negative 2 divided into 2 to check, take the derivative. Negative 2 times negative is positive 2. 1 less than negative 2 is negative 3. Let's look at 4c. I'm skipping b. Let's go to 4c. 4c says minus x to the negative 3 plus x minus 1. Minus x to the negative 3 plus x minus 1. Okay. What's the first term? What's the second term? What's the rule say over there on the right? X to the n becomes x to the n plus 1 over n plus 1. So n plus 1 gives me 2. And what is the antiderivative of negative 1? X plus c. That's the limit of my Spanish, by the way. Well, maybe a word or two more, but not much. You know, you have to know words like baño and baña. And we forget in English we don't have those gender nouns. We just say bathroom. If we want to differentiate, then we have to put an adjective in front of it. Gentleman's room, ladies' room, guys and dolls, or dudes and dudettes, or, you know, some labels. In Spanish, the gender goes with the word. So after you've had dos equis, you may forget that. Hopefully they send you to the right place. Okay, let's skip down and say number 10. 1/2 x to the minus 1/2. 1/2 x to the minus 1/2. Antiderivative with respect to x. What's one more than minus 1/2? Come on, simple arithmetic. Positive 1/2. And what is positive 1/2 divided by positive 1/2? 1 plus c. And let's skip over to 10c. It says negative 3/2 x to the negative, what, 3/2? Oh no, negative 3/2 x to the negative 5/2. Negative 3/2 x to the negative 5/2 with respect to x. What's one more than negative 5/2? Negative 3/2. X and negative 3/2. Divided by the new exponent. The old coefficient, negative 3/2, divided by negative 3/2 is 1 plus c. What looks good? Let's look at number 14. Pi cosine pi x. Pi cosine pi x. When someone gets to an answer, let me know. Oh, by the way, guess what your calculator does? Your TI-89s. If you go to F3, and you're in radians since we're doing trig functions. F3 line 2. Type in pi cosine pi x, comma x, close parenthesis.
Sine pi x.
Ooh, how about that? Sine pi x. Check it. Plus c. Derivative of sine is cosine, but chain rule, pi x would give me the pi. Pi cosine pi x. Okay. Well, let's get a little harder. Let's look at number 15. Secant squared x. Go down your list of trigonometric functions. what trigonometric function has a derivative equal to secant squared? Hmm? Derivative of the sine is cosine, derivative of cosine is minus the sine, derivative of the tangent is derivative of tangent secant squared, so what's the antiderivative of secant squared? It isn't hard, folks. There it is. Recycling. Can you spell C-C-I? Let's do it here. C-E. The chemical symbol for cesium. Isn't that right? C-E is cesium. You cesium and you solvesium. That's the name of the game. Let's do one similar to this. Integral tangent squared x dx. This one you have to be a little creative. You have to go to one of your Pythagorean identities. Your fundamental Pythagorean identity, cosine squared x plus sine squared x equals 1. If I divide everything by cosine squared x, I get 1 plus tangent squared x equals secant squared x, or tangent squared x equals secant squared x minus 1. So I can rewrite this as antiderivative secant squared x minus 1 close dx. And we know both of those. What is the antiderivative of secant squared? And what's the antiderivative of minus 1? Well, minus x. Doesn't matter whether it's C, any constant. This is 76 times some other constant, still a constant. Still an arbitrary constant. Okay. See how much fun this is? But you also notice that's dependent upon how well you do derivatives. The better you know derivatives, the better you know antiderivatives. So, let's look at, let's see if I can find one that I want to look at. Oh, number 41. T root t plus root t all over t squared. T root t plus root t all over t squared dt. If I have a plus b over c, can I write this as a over c plus b over c? So why don't I do that? This is because it's integral t to the 3/2 over t squared plus t to the 1/2 over t squared dt. Do the algebra, integral t to the minus 1/2 plus, I said integral, let me use antiderivative, plus t to the minus 3/2 dt. So what is the antiderivative of t to the minus 1/2? What's one more than minus 1/2? It's positive 1/2 divided by 1/2. Oh, which is times 2. 2t to the 1/2 What's 1 more than negative 3 halves? 1 more than negative 3 halves? Negative 1 half. Divided by negative 1 half plus C Now, since the original was given in radical form, I think I'll give this answer in radical form. 2 times radical t minus 1 over radical t, close, plus c. Or for emphasis, CC. I lied, I knew a little more Spanish than I read on. But not much. Believe me, not much. Yeah, I probably know enough to get thrown in jail in 30 different languages. But not enough to talk my way back out. Number 23. 2 over the square root of 1 minus x squared. 2 over the square root of 1 minus x squared. Antiderivative with respect to x. Go down your list of derivatives and find one whose derivative is or has the square root of 1 minus x squared in it. Sine? Not sine. Derivative of sine is a cosine. But you're on the right track. Not the sine, but the inverse of sine. Twice inverse sine of x plus. That's a big C. Have to keep it entertaining occasionally, not every night. Okay. Turning page, looking at some. Okay. 79. I'm only going, I don't want to do 7. They give us the answer. They ask us to verify the answer. Okay, we'll do that. The problem is dx over a squared plus x squared. Antiderivative. Dx over a squared plus x squared. And it claims this is 1 over a, and they'll do absolute value. Inverse tangent x over a. Plus. That's a little c. Can't see that one. Plus c. Assume A is positive. Derivative of this, checking it, derivative of the inverse tangent is 1 over 1 plus x squared, but here x squared is x over a, times the derivative of x over a. Multiply through by 1 over a. I get let's multiply through by 1 over a squared. That's not. What is, I've gone daffy here. What number is that? Number 79? Yeah. Okay. 1 plus x squared times derivative of x over a, which is 1 over a. If I multiply through by a, oh, I have an a squared down here. So if I multiply through by a squared over a squared, in the denominator I get a squared plus x squared. In the numerator I get, looks like I get a. What went wrong? So, oh, but I started with this. Oh, so if I start with start with 1 over a tan inverse of x over a, then I get 1 plus x over a squared times this 1 over a times this 1 over a, which gives me 1 over a squared, which we multiply through and we get 1 over a squared plus x squared. Okay. So it is verified. Okay, number. What looks good in this list? Number 61. 1 over x minus 5 over x squared plus 1. Over x minus 5 over x squared plus 1. And antiderivative with respect to x. Piece at a time. What's the antiderivative of 1 over x? Natural log, absolute value x. What is the antiderivative of 5 over x squared plus 1? What's the antiderivative of 1 over 1 plus x squared? What did we just do on the right? Rolling C. Like if we had a C in Oklahoma, it would be rolling right now because of the high wind.